Okay, guys. This is our last lecture. By now, your brain, your head was full of ideas, I'm sure. But the last bit of idea is at least certainly equally exciting. And if you think deeper, we start the week with Professor Sokolov, gave us the big picture of the whole world. And now we go to the small world, the nano world. And Professor Riccietta will be talking about nano-engineered reactive materials. So Dr. Yeda is, we like to claim him as ours, a Princetonian, that did his graduate studies at Princeton, both in chemistry and also in our department. And then after a while, eventually he is now at Penn State, a professor in mechanical engineering. He's truly a man of many talents. Certainly in chemical kinetics. Those of you who work on hydrogen-oxygen mechanism would certainly know that the mechanism he initially developed with Professor Dreyer. And then for some time now, he's been involved with material synthesis and the reactive materials. So, yeah.
Okay, Ed, thank you very much for, first of all, inviting me here to give a lecture on some of the work I've been doing over the last 10 years. And as Ed mentioned, the topic of the work is on nanomaterials. And particularly what I'm interested in is showing you how one can start looking at how nanotechnology and combustion can work together. My interest actually started in this work while I was still a research staff member at Princeton. While I was at Princeton, obviously I read Professor Herb Glassman's book and all of his papers on metal combustion, and I got very interested in doing metal combustion after I got my PhD. And I continued in that area, and as a consequence, the work naturally fell into the area of nanotechnology, because the field of nanotechnology in one way starts out by looking at nanoparticles. And those nanoparticles are often of metallic or metal oxide form. And so what I want to show you today, and I tried to put this at the graduate student level, and particularly at the introductory level, how one potentially can start looking at some of these interactions. And most of us are studying combustion here as a student, and you recognize that combustion is a very multidisciplinary subject. And I think as a graduate student, it's very important to specialize in getting an advanced degree. But today, it's also very important to have some breadth along with that depth. And I hope to illustrate that, because much of my talk will move in and out different areas related to combustion, particularly materials and how they interact. Now, I won't spend a large deal of looking at flame synthesis. I want to show you how one can actually make use of the materials and start imagining how these materials can be built to actually use them to make them smart for combustion applications. Okay, and so to start this, it's a rather long lecture series, so I've tried to break it up into a number of areas, and there'll be the breakage. I want to introduce the subject, and this is really introducing nanotechnology and some of the aspects that people have seen in non-reactive materials, and then start posing questions how one might use those ideas if I were to build reactive materials. And I'll do that through the introduction. And then going back to some basics. These are textbook type material. I want to show you what's kind of known about how metallic material will react, and just give you, because it's going to be important when we get down and trying to make use of these materials at the nanoscale. And then I'll spend some time right before the break and right after the break showing you a whole host of ways in which these materials are being synthesized and assembled. And what's really some of the exciting aspects of this is to look at bottom-up approaches. Okay, and bottom-up approaches deal with self-assembly, looking at mimicking nature and seeing whether or not one can actually design materials from the ground up with a priori knowledge of what features you'd like to have in that material to accomplish a certain task. And then I'd like to spend some time after the break just looking at how these materials react, how they propagate, how they combust, and then end with showing you how some of the initial applications of nanomaterial is moving forward. So to begin this, again, at a very introductory level, I guess the question is, how small is small? If I visually look at a micrometer, a micron, it's essentially invisible. And now I'm saying let's go to the nanometer, obviously invisible as well. And if one looks at what are typical sizes of things, well, a red blood cell, about a micron in length. If I go to the nanometer scale, it's about the size of a small molecule. If I look at the hydrogen atom, it's about a few tenths, maybe a tenth of a nanometer. So immediately, if both scales are invisible already, you might ask, well, why go beyond the micron scale? And one can give a number of reasons, and there's a very nice tabletop book that Frankel and Whitesides has published in the last couple of years, and they give a number of very interesting applications of where nanotechnology is being used today, and I'll show you the end one is really in energy and environment. One of the other things I mentioned, I started working in this field about 2004, and I find myself more and more nano meaning an adjustment of eyes. And so, as one starts looking, the first area in which George Whitesides really looks at is microelectronics. Okay, if we look at microelectronics, we're looking at essentially computers and the use of nanoscale material. And if you basically look at these systems, you can see that today transistors, if you look at their structure internal, there's a significant amount of nanoscale structure. If you look at, for example, the connecting wires, they're less than 40 nanometers in dimension. This is equivalent to having 100 gold atoms end to end, so very small features. And it's quite amazing, that we can even build these devices, let alone mass produce them in the quantity that we do. The second area he brings out is essentially microbiology. The smallest living unit, obviously, is the cell, and as I mentioned, the cell's on the order of a micron. If one looks inside a cell, it's a very complex functional structure. If, for example, you look at the chromosome, it's essentially consists of a meter-long DNA molecule that's intricately wound around a proton spool, and that's then fit into that cell. And so it has a significant amount of structure, and by studying that structure, one can learn a lot about life in itself. Another important area has been the ability to move to these dimensions and start doing physical measurements. It's really been the advent of these tools that has led one in the exponential growth in nanotechnology, since the tools that are used now are basically based on scanning probe microscopes, which basically use a totally different principle than, say, an optical microscope. A scanning probe microscope is basically based on having a cantilever, and at the end of this cantilever having a tip that comes to a point that maybe has a dimension of a few atoms. And one brings this cantilever very close to a surface, and one measures the attractive and repulsive forces to map out the topology of each atom. And so one can actually start studying the structure of these systems very well. The unique properties of small materials. This is really from a chemical engineer or a combustion engineer. One of the features that I hope to bring out and show you today, but just to introduce it here, if, for example, one looks at a cup of water, there's a million water molecules in that cup. But if you look at a 2 nanometer droplet, there's only about 1,000 molecules. And what this means is, as I start shrinking the size down, more and more of the atoms and molecules are located on the surface of that feature. Okay? And as a consequence of that, the material starts to behave more like the surface molecules than the bulk molecules. And what you find is the surface molecules have less coordination, they have more dangling bonds. And so their energy characteristics, their physical properties change from the bulk material, and you can start making use of a lot of those features in terms of how they react, in terms of reactivity, and even their mechanical properties. A couple other areas which Frank L. White has noted is materials themselves. If I think about materials, particularly say at the molecular level, at the atomic level, we really know quite a bit about structures of molecules. And in fact, you know, if I was a synthetic chemist, I could probably give you the rules and tell you quite a bit how to synthesize a particular molecule. If I go to the other extreme and I look at, say, things larger than a micron, go to the macroscopic level, I know basically the bulk behavior of materials, their mechanical properties, their physical properties, and obviously if I want to build something, I can obviously build a bridge, a building. But the question comes back, suppose I want to work in between at the nanoscale. How does one actually build systems with length scales of a nanoscale? So somewhere in between the atomistic scale and the macroscopic scale, there's still a large unknown in terms of how to work and assemble things and work with those. And that's really what's brought out here. And what one finds is there's a lot of features that are really controlled at this sort of mesoscale. For example, the grain characteristics are really controlled by the nanoscale features, voids, behavior of essentially cracks, tips. And this really has a lot to do then with how materials function at the macro scale. And understanding this can be very important. We're also learning that we can make new types of materials. As I said, the idea of actually starting to self-assemble these materials and making them functional for a particular task. And I keep bringing up the word here, trying to make the materials smart from the beginning. Another area for looking at nanotechnology, obviously, is quantum phenomena. We recognize in the world today, again, going to the atomistic level versus the macroscopic level, we're going from essentially a continuum level to a discrete quantized level. But somewhere in between, that physics is blurred. I mean, how do we go from this quantized world to this continuum? And by studying the nanoscale, maybe one can actually start learning how that blurring can be better understood. A big area of promise in nanotechnology has really been in the medicine field. And you're starting to see some progress here. But this is of particular interest because, as I mentioned, the cell, as I said, is about a micron. And the internal structures have nanoscale features. And the reason it's so interesting in nanotechnology is I'm working with material at the same size as the cell itself, or of that order of magnitude. And so can I start thinking about building nanorobots to actually deliver drugs, to basically kill cancer cells and things like that? And there's actually been quite a bit of work in some initial studies that are being done here. For example, the idea of using iron oxide nanoparticles and coating them with peptide and having them essentially get attracted to cancer cells. And in doing that, I can make use of MRI and have a significant better imaging process and get better detection of cancer. There's also been studies where people are starting to look at carbon material or metal oxides like iron oxide or carbon nanotubes as a means, again, with a particular self-assembly on the outside to basically look out cancerous cells, and by then locally applying heat to those nanoscale features, actually killing the cancer. So there's a lot of promise here, and again, there's a long ways to go. And finally, then I come to more of the areas of interest in this group. And already, there's actually a significant amount of work in the nanoscale area, particularly with regards to catalysts. This is a very big, booming field. The chemical industry has been using nanocatalysts now for years in terms of making, obviously, refining fuels. And you're starting to see, and what I'm going to spend some time talking about is the application to energetic reactive materials for different purposes. In terms of the environment, nanoscale material shows up all the time. I give a simple example here, where obviously as seawater evaporates, one's left with salt crystals that are being formed. They're initially of the nanoscale. Obviously, they affect cloud formation and things like that. Are there risks? There's certainly risk. There's still a number of safety concerns about the dimensions of these features and how they interact with humans. But it's a very interesting field. But I do want to say you know, there's nano, you hear nano, a lot of hype. It's a buzzword, but it's definitely not the answer to all of our materials, and it may not solve all of our reactive issues that I want to talk about. But I think it potentially could be a game changer, in particularly energetic and reactive materials, particularly if we can control it at the level and do some of the synthesis that I'll show you in a little bit. And I take this out of Whiteside's book here. Basically what he's saying is, again, you know, nano is very popular today, but it's still really the larger scale features that one has to work with to solve many of the problems. And another way maybe to interpret this, a lot of the work in nanotechnology is still pure science, and what we need to do is move this pure science and some of the developments into application areas. And I think that's what a lot of the goal is. So I want to end this with really asking the question, well, is nanotechnology new? And what you find is obviously it's not. I mean, it's been around for thousands of years. It shows up all the time. In the steel industry, as one goes through, say, a carburization process, a dusting process, it's, you know, for many years they've actually been making carbon nanotubes off the surfaces of steel, and they haven't even known it. And what's really brought this ability about, as I said, is the advancement of these new tools and able to inspect at this length scale. And I show one other case here, and that's essentially the Lycurus cup. And this is, again, very much a novelty, showing some aspects of nano features that have been around for thousands of years. This actually goes back to the 4th century. And what I'm showing here is essentially a glass cup. And from the outside, if you illuminate it from the outside, you get a jade color here. And if you illuminate it from the internal or the back side, it actually glows red. And so this was a very interesting topic over the last 10 years as to why this glassware actually had this feature. And if you actually start looking at it, and what people have done is they've disassembled the base here. When they disassembled the base, they actually got some chips off it, and it was given to some people who had access to TEMs and AFMs, and they started to look at what was really trying to characterize the material. And what they found was, when this material was actually being formed, they actually had colloids of gold and silver alloy nanoparticles, okay, and about 50 nanometers that were dispersed throughout the silica dioxide. And what here's, for example, is a picture of one of those particles that forms this colloid throughout it. And what happens then is that the silver in this nanoparticle actually is used in the reflection to reflect the green, whereas the gold actually transmits the red color here. And what's important here, you know, this wouldn't have happened if I just added gold and silver at some large scale. It's really the fact that it's in a colloid form of this very small scale. Okay. Okay. So, why combustion and nanotechnology? What can we get out of this, and what can we do with it? Well, I think the first thing I want to do is show, you know, that there hasn't been a considerable amount of increase in research in this field over the last few years. And what I did here was just pick out a few keywords, and I did essentially a Google or a literature search on it, picking the word nano, fuel, propellant, energetic material, explosive. I did not pick the word catalyst because I didn't. If I would have picked catalyst, the numbers, nano catalyst, the numbers would have been exceedingly large, and they also have the same exponential trend. But what you find over the last 10 years is there is an exponential growth in the number of publications that you're coming out with, and you start asking, well, where are the publications coming from? Well, most of them are coming from the USA and China, and there's a good bit in Europe where there's been a number of studies as well. Okay, so let me show you some of these characteristics that we want to make use of. And I started to mention these in the previous slides here. This is an example where I go back and I look at a nanopart, and what I told you was that as I shrink the size, more and more of the particles are located on the surface. And so what I'm showing you here is really looking at some iron crystals and making a plot as a function of particle size, the number of surface atoms versus the number of bulk atoms. And you can see here, when I start to get below about 10 nanometers, this ratio changed dramatically, okay? And why this is important, as I said, is because the surface atoms have a lower coordination. They have more free dangling bonds. Their physical, thermal, and mechanical properties change relative to the bulk material. And as I do this, then the particles start behaving more like the surface atoms than the bulk atoms when they're larger here. Now, I can give you an example of this right away. If I take a look at gold itself, at the macro scale, gold's not a very good catalyst. If I shrink it down to a nanoparticle, it's actually a very good catalyst. Okay? And so what you're seeing is these surface properties actually changing in the way the material behaves. Another example, here's showing some, in terms of the thermal properties, how the thermal properties might change. I'm showing some tin nanoparticles here. On the left-hand side here, again, it's a function of particle diameter. I'm showing you how the melting temperature changes. And you can see, again, starting out very close to the bulk melting temperature, about 500 K. As I start getting down about 20 nanometers, the melting temperature starts to fall off dramatically. If I look at the heat of fusion, the energetics for this to occur, you can see that the same sort of trend in terms of the energetics falling off. Now, obviously, these are actually from experiments here. There's been a lot of molecular dynamics calculations done. I put a couple here. Don Thompson and Vigor Yang have actually looked at aluminum particles doing some MD simulations. And again, if I look at an aluminum nanoparticle, what I would find in terms of its melting temperature, the bulk material melts about 937 Kelvin. If you shrink it down to about a 5 nanometer particle, the melting temperature drops about 400 Kelvin. Even more interesting, if I take a look at that thin oxide layer that passivates the aluminum particle, its temperature, where it typically melts at the bulk size, is about 2,300 Kelvin. If I shrink this down to the same 5 nanometer particle of aluminum, its oxide melting temperature drops to 1,300 Kelvin. What I'll show you in a little bit is those physical properties that end up being very important in regards to how, say, aluminum might burn. So if I can change the melting temperature of the oxide from 2,300 Kelvin down to 1,300 Kelvin, and even the melting, I'm going to have different ignition characteristics and a whole host of characteristics to deal with. In many respects, again, the reason these features are showing out is just because of the excess energy in the surface atoms and how that energy is being manipulated. If I look at the nanotechnology community, some of the goals over the last few years is one, seeing there's been significant achievement in the molecular sciences field with the goal of actually command of chemistry over all length scales. And this has actually been shown up in a number of ways, but a few examples show up, for example, in the structural determination of a number of biological systems. And I'd like to give you a couple examples here of that. And before I do that, let me point out a couple other features of some nanoparticles. Obviously, as I mentioned, as I shrink this down, the specific surface area gets bigger relative to the volume. That allows more reactivity. The catalytic activity, I showed you how the melting temperatures change, sintering characteristics change, optical properties change as well. If I look at, say, a micron particle of aluminum or a macroscopic surface, it looks gray or silver. If you look at basically a nanoparticle of aluminum, it's black. The absorption cross-section is nearly unity, so it absorbs all the photons that are hitting the surface. And so what I want to show you now is how these features and characteristics are being identified in some biological systems. And the first system I pick out is the abalone shell. And what I want to show you here is some of the characteristics of the shell, in particular the nacre, which is really the interior of the shell. Now, why is the shell of interest in the first place? Well, from a non-reactive point of view, this shell is very, very strong. Okay, it's very hard, and so it has very interesting mechanical properties to metallurgists. And if you actually look at the structure, what you find is that this nacre actually exists of millions of alternating layers of an organic material and an inorganic material. Here, calcium carbonate. Okay, and the calcium carbonate is about 95 weight%, and the organic material is about 5 weight%. This organic material is essentially a biological ligand. Okay, it's like a hydrocarbon. Okay, And what it does is it acts like a scaffold, like a ladder, and it holds these layers of this organic material together. And if you look at the individual components, they're very weak, but in combination and in this structure, it forms a very strong material. Okay, so now I want you to imagine. Okay, imagination is probably one of the most important things for a scientist today. And I want you to imagine, take a look at, for example, the solid rocket booster. For example, the boosters that were used on the space shuttle. And ask, well, what is the propellant in that system? Well, the fuel is essentially aluminum particles. That's an inorganic material. Okay, then I have an oxidizer, which is another crystal, say ammonium perchlorate. That's another particle. And then what do? I hold those together with a ligand, a binder, which is a hydrocarbon. Okay, I want to come back here. What do I got? I got an inorganic material. Well, that's my metal. That's my fuel. I've got an organic layer. That's my binder. Can I start thinking now how I can start to assemble reactive materials here, where now I might have a fuel, a binder, maybe another fuel of a different type. It could be two metallics that I form an intermetallic reaction to form an alloy that releases a significant amount of heat. It could be a metal oxide, as in a thermite reaction, release a lot of heat. Or it could be some sort of another organic oxidizer itself that releases. But again, what I'm going to do by changing these length scales, I can change the reactivity and control of this system, when it's going to ignite, how fast it's going to burn, and how it's going to burn. Okay, so this is one example. Another example I show here, and this goes really to looking at the self-assembly of nanoparticles. And really, this field, one of the reasons it got a lot of interest was the example I showed here, was the discovery that the opal gem actually consists of ordered arrays of silica dioxide particles, which would form into certain array forms of different sizes, depending upon the conditions during which this opal gem was formed. And it's these structured lattices here that really give its unique optical properties. Okay, and it's been studied through research, and the reason people have concluded is these specific types of lattice structures get formed is because of entropy considerations. Now, what you find today in the field of nanotechnology is people are trying to mimic this process, and they're looking at forces other than entropy considerations. And I show an example here using essentially electrostatic forces. And this is where people have tried to assemble systems that look like crystalline structures in nature. And they do this by, and the examples I give here are really making use of gold nanoparticles and silver nanoparticles. And what they do is they functionalize the surface with ligands, and then they manipulate the ligands to potentially oppositely charge them so that they'll self-assemble. And if I change the number or the size of those particles, I can actually generate different forms. And I show a couple of examples here. Let me just show these over here. What I show, these crystalline structures here are actually consist of nano gold and nano silver. Okay? And what I'm showing you then is the mimic in nature. Obviously, this is a diamond crystal here. And this over here has the same structure as a aluminum diboron. Okay? And you can show a whole host of these sort of structures. So again, the question is, can I actually start assembling material with different length scales? Because if I can start assembling material with different length scales, again, length scales are going to control diffusion lengths, reaction characteristics, and I'll have a significant control over my features of my material that I want to make. I mean, and these give examples of, again, in terms of imagination, in many, many years, the idea of being able to make macroscopic material with controlling the position of every atom in that material. Now, I want to show one more example here, and this shows another idea of structures. Obviously, in combustion, if I'm working with turbulence, I recognize right now scales, length scales are very important in how things behave. But I want to go back, and I'm going to come back to these examples later on in terms of reactive materials. But I show here essentially a gecko, and this is another system that's been studied in biological systems, mainly because of its multi-scale characteristics and how the gecko makes use of those different scales. Okay, in particular, what you'll find is if obviously what the gecko can do is climb up walls upside down and maneuver very quickly. And the reason the gecko can do that is because of how his toes are actually constructed. If you look at them in close, they actually have two length scales. One begins at the very tip, forming essentially these stalks, which are referred to as seta here. And they have basically a micron scale. And at the tip of the seta are actually spatula. And the spatula then go down to nanoscale features. So this allows the maneuverability here. And it's these features that allow the adhesion through, say, van der Waals forces or capillary forces. If you actually look at the forces that can be developed at the end of these tips, they're very, very small, like on the order of 10 to the minus 7 newtons. However, when I scale it up with so many of the spatula, what I find is I can get as much as about 10 newtons per centimeter squared because of the multiplication. Okay? And so what I again ask a question here is, can one make use of multi-scales in terms of how reactions propagate and interact? And I hope to show some examples of this then later on. So again, the question of imagination. Here's one example that I show you of just based on some of the ideas that I already alluded to that can one actually do in terms of, say, making a reactive material, in terms of, say, a propellant. And I can choose different types of materials. I could look at materials with catalysis and other things. But here, I thought this was an interesting approach. If I take a look at what goes into that shuttle propellant that I just told you before, I have typically fuel particles and oxidizers of particles, right? And when I typically assemble those now, I'm like a cook. I go and I start just adding ingredients and I stir it, and I have no idea where the materials are going to end up. So I have no control over where the fuel is and where the oxidizer particles are. And what I'd like to have is a little better control of that. So I come back to, say, the nanoscale, and I start looking at my basic ingredient here. Okay? And what I'll show you in a bit, obviously, is the reason aluminum particles and other metallic particles are not pyrophoric is because they have a naturally passivating oxide layer on their surface. But that oxide layer is essentially dead weight. It's already in its final oxidation state, and it's not going to contribute any more to the energy release. So one question you might ask already, is there a way of actually passivating the surface of these small particles with another reactive material? Okay, and what I show here is the idea of actually capping the surface with, say, hydrocarbon ligands, self-assembled monolayers. Okay, and the concept of doing this is if I look at how I bond this ligand to the surface, that energy is going to be related to the ignition energy of this particle. Because when I break that bond, I'm going to start opening up an unpassivated surface to an oxidizer. Okay, so there I've got some idea of how I might start controlling ignition temperatures. Now, the hydrocarbon ligand here is essentially my binder. Remember I told you in the solid propellant I have a fuel, a binder, and an oxidizer? Well, suppose I want to make this into a nanocomposite energetic material. Well, okay, well, now I've got my fuel here in the center. I've got my binder coming out here that's covering the fuel. Suppose now I come back and I say I want to functionalize the tail end of this ligand. And I want to put some oxidizer on that surface, maybe in the form of nitrogen dioxide groups, fluorine groups, or whatever. And so all of a sudden, at the nanometer scale, I'll have my fuel, my binder, and my oxidizer. Okay? So I have a nanocomposite that could be essentially controlled in terms of its ignition characteristics and the reactivity depending on the size and the structure of this. Then I start asking the question, well, can I start to assemble these particles up to the macro scale? Okay, can I start building these up in some form that I want? And eventually the dream would be, can I build, say, this entire bulk material with structure? And I just show an example here. Suppose I could change the length scales from the bottom of this sort of reactive material to the top. So I have larger features at the top, smaller defined features at the bottom. And if, for example, I were maybe to somehow ignite the top surface of here, and this material would start burning downward, because of the larger length scales, I'd have a slower burning rate in the beginning. And as the material burns down and I transition to this region here, I would accelerate the rate and I would burn much faster. But I would know how that would happen a priori through the design process. So these are sort of some of the ideas that we're thinking about, and I'll show you the progress that we've been making there. But it leads to some really probing questions already at this stage, because again, we really don't know very much at the nanoscale, as I mentioned to you. And so what one can start asking themselves is, what might be the type of shapes of particles that would want, I've shown you spherical particles, but maybe in a system I don't want spherical particles. Maybe if I'm trying to get a material to detonate, I want to somehow be able to focus that energy as the reactive wave propagates through the material. So can I actually focus and direct the energy in a particular direction? So that may say, well, I don't want to have spherical particles. Maybe I want to have triangular particles so that some of this energy somehow could be directed. And I'm not going to go in through all these, but really we don't know what might be desirable shapes for different material characteristics, say combustion, mechanical properties, hazards issues. Can oxidizer, I've been talking mainly about metallic particles. Can I do the same sort of thing with oxidizer particles? How can I passivate them? How can I learn to control that bonding at the surface? And how should that bonding occur? At what length scales does the reaction behavior change? I mentioned already about directing. How can I affect the sensitivity of the material? Can I get the materials to detonate or deflagrate? Can I get the material to stop reacting altogether? Can I get it to basically change its speed, as I was indicating that other previous example? So really what I'm starting to ask questions is, how can I start to make these materials smart? Okay? Can I start designing them from the ground up? Instead of just getting a piece of material and asking, well, how's this going to react? Can I actually start educating and building that into the material itself? Now, before I leave the introduction here, I do want to show, I've been talking about nanoparticles, and obviously one of the bad features, and I've already started addressing how it can be fixed. But if I look at a nanoparticle itself, and I start out, say, at the micron scale, and I start reducing it, aluminum particles and other metallic particles don't just ignite in air because of this passivating oxide layer. Okay? It prevents the particles from being pyrophoric. Now, this naturally passivating layer is typically on the order of maybe 2 to 3 nanometers for relatively moderate-sized particles, say a micron or so. And as I shrink the particle down, basically this thickness of this oxide layer does not change. So what that would mean is, as I start to go down to the nanometer scale, more and more of the particle is really an oxide. Okay? So if I'm looking at the core particle, the aluminum as being my fuel, if I were to shrink these naturally occurring particles to the nanometer scale, I would find that I'm losing a significant amount of energy content in the particle. Okay? And that's why I come back to this passivation, and the capping and the coatings are going to become very important to manipulate, not only to control the material, but also to make them more reactive in themselves. Okay, so that's basically the introduction. I want to spend some time now really just going through some basic textbook material. And much of this is going to rely on simple thermodynamics. It's amazing, what thermodynamics can tell us about systems. And a lot of this is, in fact, work that Professor Glassman did early on in his career. And so let me start by first showing you some energetics of these materials and the materials that we may want to consider as we shrink down. What I'm looking at here is just heats of oxidation on a volumetric and gravimetric basis of many different metallic materials. And you can see here the ones that have exceeding the largest is boron and beryllium. Aluminum also looks very good. And when I try to combine both the volumetric and gravimetric to have both relatively high, I can see silicon is actually not too bad, and carbon itself is not too bad. Beryllium's not used, at one time it was looked at, but it's too toxic. It's not looked at before. And the combustion characteristics of boron at the microscale have been very difficult. And I'll try to give you an idea why that is. It's how they burn. But what's kind of interesting is, as we shrink to the nanoscale, under certain conditions, all these metals will start to react in a very similar way. Aluminum has generally been used the most. And so what I'm going to, throughout my talk today, in terms of looking at how some of these materials are going to be used, I'm going to pick out aluminum here. I'm going to pick out silicon. Silicon is so vastly available on the Earth here. One might ask, well, why isn't it used more? And then I'll pick out carbon, too, as another example. So I'll work with those sort of 3 different materials and show how they're being synthesized and assembled. Okay, so for some simple thermodynamics now, and as I said, this goes back to a couple very important observations and work. that was recognized by Professor Glassman and von Gross and Conway, probably back in the 1950s. But really, there's two aspects here, and I'll allude on these in a little bit more in the future slides. The first is looking at the importance of the volatility of the metal versus the metal oxide, and really the energetics of this. This will basically tell us the first order how these materials might burn. And the second really regards with looking at the energetics of the overall reaction here and asking, well, how much energy is available and what can I do with that energy? Is there enough energy to actually completely vaporize the metal oxide that's formed? Is there enough energy to vaporize the original fuel component or not? And this can be written in as an energy statement as shown here, where Q sub R here is essentially the heat of reaction. This is the sensible enthalpy that's required to raise the temperature of the products being formed to essentially the vaporization or dissociation temperature of the metal oxides that are being formed. So the right-hand side is sort of like the amount of enthalpy that's available to completely vaporize or dissociate the refractory metal oxide that's formed. And to give you some examples of how this applies to the different components and materials that I just showed you on the view graph, here's a table that one can formulate. And so again, I'm picking a number of different elements here, and I'm going to ask the simple question is, how might they react in a molecular oxygen environment? And so the first consideration I'm looking at here in this column is essentially the boiling point temperature. This is the metal oxide that will be formed after the oxidation process. And this is essentially either the boiling point temperature or the temperature of its volatilization, since many of these refractory materials actually will dissociate upon trying to vaporize. Okay. The third column, or this column here, is essentially the heat of formation of the metal oxide. And since I'm starting off, in the example I'm using here, I'm starting off from elements and I'm reacting it with molecular oxygen. The heat of formation of the product is essentially the heat of reaction of the reaction that occurs. And what I show in this column here is the combination of the enthalpy required to volatilize the material as well as raise it to essentially the final temperature here. So if I go back to the first criteria on the previous view graph and I look at, say, this column versus this column, what this would suggest from energetics is that since the boiling point temperature of the metal is less than the boiling point or decomposition temperature of the metal oxide, aluminum would be expected to burn in the vapor phase. You would actually vaporize the aluminum, and the gaseous aluminum would react with the oxygen. Okay. If I come over here now and look at this number compared to this number here, what this would suggest here is this is the amount of energy that I'm going to require if I want to completely dissociate and vaporize all this final product from, say, a liquid alumina to gaseous species. And you can see that the energy available is only this much. So since I don't have enough energy to completely vaporize this, what happens is the formation and the dissociation of the aluminum oxide actually limits the flame temperature. Okay? And so I get a limiting flame temperature situation. And I can go down and apply this methodology to all the elements I show here. And if you work through here, you'll see, for example, boron, silica, and zirconium. If I first look at these criteria here, I have the opposite trend, which would suggest in this particular case that the boron would burn more in a heterogeneous fashion, where since I'm vaporizing the final product, I don't have enough energy to vaporize the boron itself, so it's going to burn like a carbon particle. Okay, there's going to be a heterogeneous process where reactions are potentially going to occur at the surface. Okay, and so to illustrate this a little bit further and to define this, this is really a classification of this process, and I again pulled this out of some of Foreman Williams' work, which really follows Herb Glassman's work. But really, there's the first discrimination that I just showed you was first looking at the energetics, whether or not the product would be in a volatile form or a non-volatile form. The second discrimination then would be to see whether or not there's enough energetics that are available to actually vaporize the metal itself, or does the metal remain as a non-volatile? And I can break this up for both sides. And then there's a third discrimination on asking whether or not the products that are being formed are soluble or insoluble in the original fuel. So for example, if I look at this first column here, I have a volatile product, I have a volatile fuel. This would be how a hydrocarbon droplet would burn, right? I form gaseous CO2, water, and I end up vaporizing my fuel. If I come over here, I have a volatile product, and I end up the energetics, I can't vaporize the original fuel, I end up having something like a carbon particle, where the carbon particle doesn't vaporize, but it forms carbon dioxide as a final product. Over here, I have my non-volatile product, but a volatile metal. This would be like the aluminum particles that I just mentioned, or magnesium. And if I look over here, in this case, both I have a non-volatile product and metal. So in this case here, I'm going to have the product being formed directly on the surface. This might be something like hafnium, how it might burn. And if I come down to this third discrimination, the importance of this is really, in some cases, how the material might burn itself as it's burning. And in particular, if you see that the product is highly soluble in the original fuel, you can actually start to get some interactions between, say, absorbed oxygen and phase changes where you actually get disruptions. And so I could have a disruptive burning process. So to illustrate that in a little bit further fashion, again, just working with thermodynamics here and showing you what one can really learn as to how these materials might burn, I'm showing you here really now looking at pressure as a function of temperature. And these calculations that I'm going to show you are just calculating the adiabatic flame temperature from a code such as the NASA equilibrium code. And I've already talked about, and this is really for aluminum burning here, but I want to show you again the effect of pressure and oxidizer on the criteria that I showed you earlier. Okay, if I look at one atmosphere here, I want to really pull out two curves. The first curve here is essentially aluminum reacting with a simulated air, or air here, so oxygen and nitrogen. And what I'll find then is at 1 atmosphere, the flame temperature is about 36 or 3700 Kelvin, okay? So that's the reaction temperature. The other line I want you to look at is this line. This is the vaporization temperature here. So if I look at the temperature at which aluminum is going to vaporize, it's about 2700 Kelvin at 1 atmosphere. So the flame temperature is higher than the vaporization temperature. So much like a hydrocarbon droplet, I'm going to form an envelope. If this is a large particle or a bulk material, I'm going to have basically heat being transported back from where the reaction occurs to the surface. It's going to vaporize the aluminum, and the aluminum is going to vaporize away from the surface and react with the surrounding oxygen. What's kind of interesting then is if I start increasing the pressure in systems. Okay, as I start to increase the pressure, one thing you start to notice is the vaporization temperature goes up at a higher rate than the flame temperature itself. So theoretically, I can get to a situation above, say, 100 atmospheres, where now the reaction temperature is less than the vaporization temperature. So no longer do I have the heat from the reaction coming back to the surface to vaporize the aluminum. And so I'm going to see at very high pressures potentially aluminum change from a vapor phase to a heterogeneous reaction. And this is in oxygen. Now I ask the question, well, suppose I was doing this in a different oxidizer like CO2 or water vapor. What I'm ending up doing here is I'm changing the energetics of that reaction, the heat of reaction. I'm actually lowering it. And what you see as a consequence of this, if I try to burn aluminum in liquid water, what I'll find is that at very low pressures, I'm back to the original situation where the flame temperature is higher than the vaporization temperature, so I could have a gas phase process. But just slightly above 1 atmosphere, I get this crossover effect to happen. So now if I just raise the pressure a little bit, I'm going to be getting to a situation where aluminum wants to burn heterogeneously with, say, liquid water, or even water in the vapor state. Okay, and to illustrate that, I show some pictures here of the effect of oxidizer and pressure on single particles of aluminum, which are at the micron scale. Okay, so here, this is an experiment where you're seeing a single droplet that's being ignited by a laser here. It's falling, and what you see, that in this particular case, the Grashof number is very low, the Reynolds number very low as this particle. So this is a strobed image. You're seeing the same particle here. And what you can see here then is the aluminum particle here is vaporizing. Aluminum is diffusing outward, and this is the spherical reaction zone or flame that sits around the particle that gets a temperature close to 3,700 Kelvin, 3,600 Kelvin. The heat is fed back to the surface, and I vaporize the aluminum. And the oxidizer out here, which is molecular oxygen and air, diffuses inward. So this scattering you see out here is actually aluminum oxide being formed in the reaction zone. So the first question is, well, suppose I change the oxidizer to steam, okay? And I go back to what I showed you on the previous view graph. Well, you can see the structure of this flame has changed drastically. In fact, now I don't have this envelope flame, and what you see, even at atmospheric pressure, the reaction is occurring very close to the surface, if not on the surface. And these bright spots you see here are aluminum oxide being formed on the surface in a high concentration. And because of the different surface tensions of the molten aluminum and the molten alumina, it basically forms caps, and as the droplet spins as it's falling, it throws the oxide off the surface. So already you can see the mode changing here. And I also show now the pressure effects using molecular oxygen as the oxidizer. Here I'm going from 1 atmosphere to 2 atmospheres to 60 atmospheres, and again you can see it's the same size particle originally, but the flame envelope is getting closer and closer to the surface, and if I were somehow able to do this experiment at higher pressures, the reaction would move right to the surface. So again, showing you how these characteristics, and this will become important as I look at different oxidizers in different systems and later on. Okay, this is another interesting plot that Professor Glassman and Paul Pappas actually looked at early on. And this is the idea of looking at this limiting flame temperature concept and these metal reactions. And what I've done here again is I'm looking at essentially an equilibrium analysis where I'm changing the amount of energy that I'm adding to the initial reactants in this equilibrium analysis, either by adding energy to the reactants or I'm removing energy. And so if I look at the case of 0 here, this is when the reactants are, say, at 298 Kelvin, and these calculations are at 1 atmosphere. So this would give you basically the flame temperature that I showed you previously, and this would be the composition. And what you can see here, under these conditions, some of the condensed phase alumina has been dissociated, and I'm forming species in the gas phase as I dissociate. Now look what happens when I start to take energy away from the reactants. As I start to take energy away, the temperature stays constant, and you can see the amount of alumina in the products increases and the gas phase species disappear. Until I get to this point out here, where at this energy level I take away all the product is condensed phase oxide. If I add energy to the system, you can see the temperature still stays the same, but the amount of alumina changes, and I start getting more and more gas phase species until I get to an energy level out here. And at that point, all the condensed phase material disappears and the temperature starts to rise. So what you're seeing here is essentially the reaction temperature sort of being controlled by a pseudo-phase change of the final product, okay? And this is sort of the concept of this limiting flame temperature. Now to illustrate that experimentally, these are some experiments that I did with Fred Dreyer here at Princeton before I left. These are, again, looking at single particles of aluminum burning, and what we're looking at here is doing essentially some laser-induced fluorescent measurements, trying to measure the smallest suboxide around an aluminum particle as it burns. And what we do then is we actually fluoresce the aluminum oxide at 2 different wavelengths, and from that we can use a Boltzmann distribution to back out the flame temperature. And what I show here, this is really the fluorescence image from aluminum monoxide. And you can see here then, this is again for a 200 micron particle, so I'm still dealing in the micron scale. This is a function of non-dimensional radius off the surface. And what you see is that essentially aluminum is being vaporized, it's diffusing outward. As the aluminum leaves the surface here, I start to form the smallest suboxide, which is aluminum monoxide. It peaks, and then it starts getting consumed, and then I start forming my final product. And the point I want to show here, unlike a hydrocarbon droplet where I have a relatively narrow peak in the flame temperature, the flame temperature here is very, very broad. It's not a complete plateau because I'm changing sort of the stoichiometry as I move across this, but you can see the plateau is very broad and near the flame temperatures that I showed you on the previous view graphs. Okay, I've been talking about basically molecular oxygen as the oxidizer. As I start moving into these other areas, we're going to look at different types of oxidizers. And one of the systems that one looks at, obviously, is, and I've mentioned this, is the concept of thermite reactions versus intermetallic reactions and how these materials might react. So say, for example, I wanted to react something like aluminum with iron oxide. And in this case, suppose I react 2 moles of aluminum with iron oxide. I could actually, if this is an exothermic process, I could actually drive the reaction to make aluminum oxide plus iron. So the reason I bring this up is because this sort of field has been very important in terms of material synthesis, using thermite-type reactions, intermetallic reactions to make certain types of materials. So say, for example, I had readily available aluminum and iron oxide, and I'm just showing this because it's a classical thermite reaction. But suppose I had those materials readily available, and I wanted to either make the aluminum oxide or the iron itself because it was much rarer or more expensive. This would show, if indeed this reaction was exothermic, I could actually use the exothermicity from the reaction to actually make this material. And this is really the area of using combustion to make materials. It's really been referred to as SHS, self-propagating high-temperature synthesis of materials. Merchanov in Russia was really one of the first persons to look at it back in the 1970s, and it's had a significant amount of growth. And in fact, it's led to a lot of the combustion synthesis work that's even done in the gas phase today in making nanoparticles. Now, what drives this reaction here, as I said, is really the exothermicity of the reaction, or in fact, it's really the change in free energy of the reaction. Okay, and so if I were to look at this reaction in particular in the free energy, I could write out, as you all know, that the change in the free energy is going to equal the change in enthalpy minus the temperature change in entropy. And if I look at this particular reaction, and you can see if I look across the reaction, the number of moles does not change that much. And what that indicates, obviously, is that this order is not changing significantly. And so at first order, the change in entropy in that reaction there may not be too significant for these sort of thermite reactions. And so I might be able to neglect that in the first order, say the change in free energy is related to the change in enthalpy or the heat of reaction of that system. And so if I look at that reaction at standard conditions, I find both the aluminum and the iron are elements, right? So their heats of formation are 0. So really whether or not this reaction will proceed is just to look at the oxides, okay? And the question here then, does aluminum oxide, is the heat of formation more negative, more exothermic than a heat of formation of iron oxide? And indeed it is, which would indicate that that reaction would proceed and self-propagate in that direction, okay? I mean, this is thermodynamically, so it has the driven force. I'm not giving you any indication of how fast that will proceed, because that's going to depend on length scales. Now, what people have done is really use this sort of concept to look at the formation of other types of materials, and that's really what I show in this slide here. Instead of looking at, say, molecular oxygen as the oxidizer here, one can actually look at the concept of making nitrides, pure metals. One can work with metal chlorides. One can make selenides. And you can do that by mixing different reactants and looking at whether or not the reaction is going to be driven exothermically in a particular direction. So what I show here is the example of suppose I want to make this pure metal element here, and I start off with some sort of chloride, metal chloride, okay? And since sodium is relatively available, I'm going to drive the reaction to form sodium chloride. So based on the concepts I just mentioned here, what I want to know, in fact, then, is I want to compare then the heat of formation of the sodium chloride versus the starting material I start with here. So if I do this on a per atom basis of chlorine atoms, what I'll find then is the heat of reactions like 411 here. And what this is saying is if I want this reaction to proceed exothermically, I could potentially choose any starting reactant over here to basically make the metallic component. So for example, if I wanted to make titanium from titanium tetrachloride, I could react it with sodium, and it would be exothermic, so it would self-propagate, and I'd end up making titanium. And I can do the same sort of reasoning if I had gaseous nitrogen, for example. I could look at the heat of, obviously, nitrogen 0, but if I wanted to make titanium nitride then, okay? So the titanium nitride has to be more exothermic, obviously, than the heat of formation, and indeed it is. So potentially I could react titanium with molecular nitrogen or sodium azide here to form the nitrides, or any other nitride up here. And this is just to show you here that one can actually mix systems and start with more available, readily available materials to end up with the metal nitrides by how one combines it, or one could actually make different types of metal oxides. Okay, as I said, again, thermodynamics, a very useful tool whether or not one can actually proceed with these sort of reactions. Okay, so why, I show those in terms of material synthesis, and again, just to give you an idea of why they're of such interest, I wanted to show you actually some of the energetics and these combinations. And so what I'm showing here on the left-hand side are some typical thermite-type reactions where I'm going to react, say, aluminum, silicon, or carbon with some different metal oxides. And over here I show some intermetallic reactions. When I react, I form an alloy. And what I'm doing is I'm comparing this with the energetics of TNT on a gravimetric as well as a volumetric basis. Now, TNT has been synthesized maybe 140 years ago. And if you look at, there's been a lot of, in the energetics community, there's been a lot of work trying to synthesize other organic energetic materials. If you were to look at, the accomplishments over the last 140 years, these numbers have not doubled here. Okay? If you look at the most energetic organic material, it's probably no more than a factor of 2 than TNT. So if I compare it to some of these systems, you can see, on a gravimetric basis, easily comparable, but even more so on a volumetric basis, these intermetallic or thermite reactions are quite significant, even with silicon reacting with the components. And the intermetallics, same sort of result. I picked this particular reaction out here because I thought maybe Gio Richards would talk a little bit about chemical looping, and I'll come back to this a little bit. But here's a case. Chemical looping is a method in terms of looking at direct coal oxidation, but without air. So it's a way of essentially artificially separating the oxygen and nitrogen from the air by oxidizing the carbon with copper oxide. Okay, and what I do then is I get my flue gas is really highly concentrated in CO2, and I don't have the nitrogen removed. And then what I do in the chemical looping process, I have a second reactor that'll reoxidize the copper back to carbon monoxide and again react it directly with coal. I'll come back to this because it's another one of these systems we're going to look at a nanoscale. Okay, now I've been talking thermodynamics. When we start talking about particles themselves, we introduce a length scale into the problem. And if I introduce a length scale, I'm essentially introducing a time scale for mass and energy transport. And again, just looking at simple concepts here, what can one learn as to how these materials might start behaving as I start going from a large length scale down to a very small length scale? Well, typically, if I look at this from two extreme limits, one can look at a situation where I have very, very fast transport of mass and energy, and what's limiting the process then is really the chemistry. And so in those sort of cases, since I have very fast transport, my mass and energy is moving freely around, I lose all spatial gradients in the surrounding environment around, say, a surface. And so what you see here is if this was a surface reacting here, I potentially would have my oxidizer diffuse very rapidly up to the surface. It would react and be transported right away as products, and I'd have very little fuel out here. And the temperature distribution across the domain would be very simple, because even if this was a very exothermic reaction on the surface, I would have very high transport rates that could start to bring the temperature down close to the environment temperature. Now, if I go to the other extreme where I start to basically slow the mass transport down, okay, what I start ending up is a situation where I can no longer get rid of the gradients in the environment around it, and I start to see spatial gradients. And under these conditions, then, my transport is what's rate limiting, and I have what's referred to as a diffusion controlled process versus a kinetically controlled process. And I show two examples here. In this particular case, I actually have, much like the aluminum particle that I showed you, I have a surrounding envelope flame. And so the fuel is leaving the surface, and I have oxidizer coming in, and it's these processes here that rate limit the process, and I have very fast chemistry when they come together, and I form a diffusion flame. Now, I don't have to have the gas reaction occurring in the surface. I could still have a diffusion controlled process on the surface, but I'd still end up having spatial gradients, and this process would still be diffusion controlled. Well, if I look at these systems, and this is what's been done traditionally in textbooks, I can go back and solve the one-dimensional conservation equation for species and energy, and I can come up with solutions for what these profiles might look like. And once I have those profiles, I could actually calculate burning times, how fast these particles might react. And if you do that, what you'll end up with is some of the results I show here. Again, just looking at two extreme cases. And again, I just want to pick out some of the qualitative trends, and these are sort of the trends that you should go away with. But if you look at, say, the diffusion controlled case, and again, you go through and you integrate the equations, you'll get an equation for the mass burning rate. I can integrate that equation from the initial size of the particle to letting it disappear, and I can then calculate a burning time. And what I find then is that burning time, if I have that diffusion controlled situation, will scale with what's on the right-hand side here. And this is the case where I have that envelope flame around the outside. So you can see it's proportional to the original diameter of the particle squared. The density of the particle, rho d here is essentially the density of the gas, the diffusivity in the surrounding gas. And B here is the mass transfer or Spalding number, and essentially the driving force for the system. I can change this situation, so suppose now I have the surface as being where the reaction occurs, but it's still mass transport controlled in the surrounding. I again find that the time here for the burnout is proportional to the original size of the diameter of the particle squared. Okay, and the driving force is still now related to how much oxidizers in the surrounding environment. If I start looking at the opposite extreme case, I recognize that the rate at which this particle is burning is related to the rate of the surface reaction, and I can go through and derive an equation in for, again, the mass consumption rate of the particle, integrate that out, and I can attain, again, a very simple expression for how long it would take the particle to be consumed under a condition where it's kinetically controlled. And what one typically finds then is now this time is related to the initial diameter to the first power. In addition, you find in the denominator here a pressure term, and this is essentially the rate constant of that chemical reaction. So this is going to be highly temperature dependent here. Now, if I ask the question, well, you know, what's going to govern when these two processes change from one to the other, I might, you know, define some sort of Damkohler number where I look at basically a characteristic diffusion time to a characteristic kinetic time and just take the ratio of these two terms. And I took these terms here. And if you do that, you get an expression like this. Okay? And what this tells me then is if I'm looking at large diameters or very high pressures, I'm going to basically have a diffusion controlled situation. If I'm looking at very small diameters or low pressures, then I'm going to have basically a kinetic controlled situation. So what this is telling me is if I start off with a large particle and I start shrinking it down, I would expect it was changed from a diffusion controlled process to a kinetically controlled process. Rho d here is going to be the first order independent of pressure. So I can use this to start analyzing how, when I get to a nanoscale, the particles may react. There's another important time scale that comes involved here, and this is essentially looking at the Knudsen number, which is a comparison of the particle diameter compared to the mean free path of the molecules in the surrounding gas. And when these become of the same order, what that means is that now I'm leaving essentially this continuum where I'm assuming the particle has much larger dimensions than the spacing of the molecules and the collisions are frequent. But now I'm coming down into a free molecular regime when they're of the same order here. And one can estimate the mean free path from essentially kinetic theory. Here you see it's 1 over the number density. If I use kinetic theory for a simple billiard ball situation, what I end up with is an expression like this. So you can see that the mean free path is proportional to 1 over the pressure or to the temperature to the 1/2 power, and I can put that here. Okay, so what that means is if I'm at high temperatures or low pressures, I'm going to be moving towards this free molecular regime. Okay, if you do a back of the hand calculation and you assume I'm starting with a particle of about 100 nanometers, 1/10 of a micron, what you find is you have Knudsen numbers greater than 1 for the entire temperature regime relevant to combustion, from room temperature all the way up to typical flame temperatures. So for 100 nanometer particles and smaller, I'm starting to get into this regime where I've got to start asking myself, is Fick's law, which is describing this mass transport on a continuum basis, is that still valid or not? Okay. Now to illustrate some of these points, well, yeah, before I do that, let me come back here. as I said, as I start to shrink the particle down, okay, what I'm going to find is it becomes kinetically controlled, as I just showed you. And when the particle becomes very small, what I'm going to start to see is the particle, because it has very little mass, is going to start to assume the same temperature as the environment. So the environment now is going to start controlling the temperature of the particle. Whereas in this region over here, the particle's burning, if this was aluminum, this flame temperature out here is 4,000 K, and it's this temperature that has the biggest influence on what how the particle's burning. But now, so it's really the flame temperature. Here, since I don't have any localized reaction out here, it's really the environmental temperature. So now I ask another question. Suppose the environmental temperature is less than the vaporization temperature. How's aluminum going to burn now, right, at a nanoparticle, right? So I'm going to have another two regimes here, depending on whether or not the particle, the environmental temperature is above the vaporization temperature or below the vaporization temperature. Okay, and it's going to be totally not being constrained by what the particle's doing itself. And if that's the case, one can look in, say, the chemical engineering literature and look at basically what's been done in terms of looking at, say, how coal might react in terms of a shrinking core model with an unchanging particle size. So this would be the case that I was just illustrating. Suppose now I'm burning aluminum nanoparticles, the environmental temperature is below the vaporization temperature. I know the product is a condensed phase compound, and so it's going to be typically formed on the surface. And what I'm going to have now in these problems is I'm going to have essentially two diffusion layers, one in the gas phase film outside, and as the reaction zone continually progresses, this is more and more of the particle being consumed in the condensed phase. Here's the reaction zone. I'm going to have another diffusion barrier building up as the particle. So now I have the gas phase diffusion barrier as well as what's happening in the condensed phase. And again, one could go through this same sort of process, assume the particle's burning in the condensed phase here, and look at two extreme limits, either a diffusion-controlled process or a kinetically controlled process. In these cases, if you assume, again, that the entire system's at constant temperature, I need to solve the species equations. And what I end up with then are the same sort of similar expressions that I had before. If the system's diffusion-controlled, I find the characteristic time for consumption is proportional to the particle size squared. If it's kinetically controlled, it's proportional to the character size of the first power. What I want to show you here, though, is an interesting result if I look at this in terms of percent of conversion, okay, and what this means in terms of actually the rates of conversion. And really, I want you to concentrate on the plot here in the lower right. So what I'm plotting here is the percent of conversion. So this would mean that 20% of the particle has been consumed. And this is essentially the rate of that conversion at that point of the process. So if I have a kinetically controlled process, you know, what you see is this is the dependence of the rate. So it basically it decreases as I go through, sort of monotonically as I go through the particle. What I see here, if it's diffusion controlled, after about 20% of the particle's been consumed, the reaction rate is going to fall off significantly. And so what happens in these sort of situations where I have this shrinking particle, one has to ask the question, do I have enough residence time in my, or characteristic time to react the entire particle? So, you know, you may think going to nanoscale could be a benefit because the amount of mass I got to consume is very small. But if I get into a regime where it's diffusion controlled and I have a condensed phase reaction occurring through the entire system, I may actually end up losing in the end. Okay, so let's take a look at some of the results that have actually been found. And I'm using aluminum here as an example still. Okay, and so these are actually some experimental results on particle burning times. And what you see here for very large particles, 10 microns and above, if I go through, and this is some work that Merle Beckstead did in terms of gathering all the available data on particle burning, he was able to sort of correlate this data, and he found it correlated with about d to the 1.8. So it's pretty close to 2. It's a little bit different. His argument for this was, well, you know, depending on how the particle burns, I do form a little bit of aluminum oxide on the surface, and that starts to cover some of the surface, so I don't have the entire surface available for vaporization. But indeed, this looks like it's a diffusion-controlled process. If I start going down to about 10 micron, then what one sees is actually the slope changing, just as one would expect, where I potentially am now changing from a diffusion-controlled process to a kinetically controlled process. And this is some work that Tim Parr has done at China Lake that I'm reporting here. Others have done it in terms of Nick Glumack have done some shop tube experiments on very small particles, and they find very similar results. So the one thing I also want to note, remember I told you in the diffusion control, the important temperature is the flame temperature around the particle. Okay, and so it's not too sensitive if I vary the environmental temperature. If I get to these very small sizes and I start to vary the environmental temperature, since kinetics is controlling, you can see that essentially the burning time changes as I lower the temperature. The points up here are some work that Mike Zachariah did in the flow reactor at very low temperature at about, I guess, 700 or 900 Kelvin in that range. And you can see that the rates of the burning times get longer and longer as I lower that temperature. There is an interesting result here, and it's still a result of quite controversy. If I actually take a look at the exponent for this work of Tim Parr and even the work of Nick Glumac, I'm much less than d to the 1. In fact, these are about d to the 0.3. And so, you know, originally when one looks at it, one might ask, well, can I actually do these experiments very accurately? Because, you know, I'm not going to have a size distribution of particles. First of all, that's going to be exactly a tenth of a micron. And these particles being very small, they have a lot of surface area. They tend to agglomerate. So am I actually looking at individual particles as they're burning here? I could also be asking, well, do they go to completion from the argument that I just showed you? Because in these cases here, I do have a regression surface in a condensed phase system. But there are other theories as well that are coming out that could partly start explaining this, and some of them have to do with looking at whether or not I'm still in a continuum regime. There's been some analysis of looking at how that reaction front propagates in the condensed phase, and if you assume it's got a fractal front as it propagates, you get an increased surface area as you regress, and that increase in surface area can actually explain this d to the 0.3 or a value lower than. So it's a topic of concern still in this area as I get to smaller and smaller particles. Here's some results at looking at ignition temperatures of particles, again, as I change particle diameter. And what you're seeing here is that I'm starting out at very large particle diameters. Again, we're looking at aluminum, essentially ignition. And what you're seeing here is essentially ignition temperatures. For very large particles, micron above, the ignition temperature occurs very close to the condition where the oxide initially melts. Okay, and what that does then is because of the difference in surface tensions between the molten aluminum and the oxide, I basically have caps being formed. I open up free surface. So intuitively, one would expect, and that would be the condition where these large surfaces would start to ignite. And what the data shows then, as I start to shrink the particle, the ignition temperature starts to drop lower and lower until I get to very small particles. I actually start to approach the temperature at which the now aluminum melts versus the aluminum oxide. And the concept here is as I shrink the particle down, what I'm getting is more divergence in stress in the original material. And as the aluminum potentially melts, I'm actually stressing that oxide layer before it melts, and I'm actually internally building up a significant amount of pressure. That pressure potentially could crack the surface, create pores, and lead to ignition at a much lower temperature. I want to show some other examples of what people have observed experimentally for nanoparticles, and I'll come back to what I was just talking about. But this is a case, again, now looking at nano-aluminum. Instead of doing combustion experiments, these are results of experiments that were done in a thermal gravimetric analysis. So what one's measuring is the mass accumulation as one changes the reaction temperature. And this is looking at the exothermicity of the reaction through a differential scaling calorimeter. And so here the oxidant is CO2, but it could have been molecular oxygen. It doesn't matter. You'd see the same results. And what you see are results as one changes from the micron scale down to the nanometer scale. And what you're seeing here then is if I look at micron particles and I look at the energetics, what I find is slightly above 650 here, I see an endotherm here. This is when the aluminum starts to melt. And then as I go to higher temperatures, I start to see my exothermicity occurring, and I start to see the accumulation and the buildup of the alumina, so I'm getting a mass gain. As I start to shrink the size of the particle down, you can first of all see, just as I showed you on the previous view graph in the combustion experiments, the temperature at which the aluminum starts to react drops. But what's very interesting is at the very smallest particles here, I'm actually getting to a situation where the reaction occurs below the melting temperature. So that suggests two things. Either it suggests I'm having a direct solid state reaction occurring between the oxidizer and the aluminum, or I've effectively, as I showed you here, I'm starting to also affect when the melting temperature is changing because the particle size is getting smaller and smaller. Okay, so again, starting to show you the ability to control reaction characteristics as we get to these small scales. Now, there's been interpretations as to how this process of these particles are being ignited. I'll show a couple just to give you a flavor for what people are thinking. As I said, one of the theories is that as I get to these small particles, I build up a significant amount of internal stress. The pressures get very high internally, and I can essentially fracture that surface during, say, the melting process. This is some work that was done at NJIT from Ed Reason, and what he's done is a significant amount of, again, TGA experiments. So this is from slow heating rate type experiments. And what he's attributing the ignition process to is, again, through obviously exothermic reactions, but the fact that the phase of the oxide changes significantly as I raise the temperature of the system. So if I were to start off with, say, an amorphous oxide here, what I would see at low temperatures is as the, say, aluminum cations would diffuse through the amorphous oxide, I'd get a reaction with the oxygen, and I'd start to build this layer up little by little of oxide. It would be amorphous, and the temperature would start to rise. And what you find is that amorphous oxide has a stability thickness of about 5 nanometers. And if the temperature here raises quicker than I can build this layer up to 5 nanometers, what I see is when I transition from amorphous to gamma aluminum oxide, since there's a change in density, what I can do is actually start creating pores in the oxide coating, and this allows then direct oxidation from the oxidizer out here with the aluminum. And that can accelerate then the oxidation rate, raise the temperature further. As I go through this, I can change through different additional polymorphs here, delta and theta, and eventually I'll get up to basically alpha aluminum oxide, and the exothermicity will bring me to essentially the melting temperature. Okay, so this is obviously one theory. In some of the work that Mike Zachariah has done in some flow reactor studies where he's done single particle mass spectrometry, what he does is he builds a flow reactor, he in situ creates the aluminum particles, he passes the particles then through a reactor at different length, at different temperature, and he lets the particles react with, say, an oxidizer. He then, in a mass spec, collects the particles one at a time, he ionizes them, and then he looks at the elemental composition. And by looking at how much aluminum is there versus oxygen, he can look at the extent of reaction for a given residence time. And he can do this for different sized particles. And indeed, what he finds is as he changes the particle size to smaller and smaller particles, he gets an enhanced reaction rate. Okay, so the reaction rate, again, is going to be particle size dependent here. And you can see this in terms of an effective activation energy. He's effectively lowered the activation energy by going to smaller and smaller particles. He's actually used this data then to back out an effective diffusion coefficient, because when he started to look at the effect of particle size on essentially the reaction time for half of the consumption, what he finds is that his results look like he's now in a diffusion-controlled regime versus a kinetically controlled regime. So here's a situation now. If I start off with a very large particle, I'm diffusion-controlled. As I shrink it down, I'm probably going to get to a kinetically controlled, and potentially now it's going back to a diffusion-controlled situation in the condensed phase. What I want to show is just, I mentioned about the, people have been modeling these systems significantly, and where the future is, particularly in condensed phase reactions and looking at interfaces, is through molecular dynamics calculations. These are some results of Priya Vashishta. He's at USC. And what he's been doing is he builds up nanoparticles with billions of atoms. And he looks at then how these particles will essentially react. And I show a couple of examples here. On the right-hand side, what I'm showing here is during the reaction of a particle, what is the pressure distribution as this particle starts to heat up. And this goes back to the fact that internal pressures can actually be quite large. So what you find is the aluminum core here is under a very high positive pressure on the order of, say, a half a gigapascal. And as a consequence of that, the blue here, which is essentially the outer shell, the oxide, is under essentially a negative pressure. Okay, so you can actually get these situations where, depending on the heating rate and the size of the particle and the original thickness of the oxide layer itself, these materials can actually react differently. Dana Delot at USC has done some very nice experiments where he's actually heated the particles with different sources. For example, a femtosecond laser versus just a light source. And he's done some nice experiments where he's changed the thickness of the oxide layer. Under very low heating rates, he found that how the particle reacted was independent of that oxide layer thickness. So you would add the heat very slowly to it, and not much would happen. But if I heated the particle very quickly, the particle that had the much thicker oxide layer actually exploded and disrupted, and I had a much more violent reaction. And the anticipation is that because of the thicker oxide layer, I could hold this internal positive pressure under for a longer period of time, let the pressure build up greater, and I'd have this disruptive process, much as seen here. Just to give you an illustration, the pictures on the left here are some molecular dynamics calculations. One of the first things that Priya did was to see whether or not he could predict the thickness of the oxide layer that naturally passivates on a particle. And indeed, what I'm showing, this is showing the reaction that's occurring and forming the oxide layer thickness out here. And what you see here is a function of time. This is the thickness of the oxide layer growing, and it quenches itself a little over 3 nanometers. So it's very good to what's been measured experimentally. Some of his more recent experiments are very interesting. It comes back to what's happening in terms of ignition. He was looking at a nanoparticle on the order of about 5 nanometers with an original thickness shell on it. And what he found was, as he started to heat this particle up, what was very important in terms of the heating process, what he did is he put the particle in essentially an environment that was about 1,000 K. And it wasn't the surrounding oxygen in the environment that was important in the initial heating process, but what was important was the fact that the oxide layer itself started to have oxygen diffused to the interior core. Okay? And as a consequence of that, the composition of the particle as a whole was changing from having an aluminum core in the center and an aluminum oxide shell to something that looked like AlXOY that was distributed across the particle itself. And what that was doing was that forming the suboxide was actually an exothermic process that was raising the temperature up. So again, the idea of just by looking at some of these particles and doing these MD calculations, new interpretations on how these particles are actually burning. Okay, so what I want to do now is I tried to give you again a review. I'm going to come back to those concepts. But I want to move in, in fact, I guess we've got a few minutes before the break. Let me do a couple slides here to give you a flavor of what I want to start talking about. But what I want to do now is start to show you how one is working with small particles, how they're being synthesized and assembled. And to do that, let me tell you sort of where I want to focus is because there's been a lot of research in this area, and I'm not going to have enough time. And what I tried to do in this is add references for those who are interested to go and look a little bit deeper. But obviously, the way one creates and assembles these nanoparticles and nanomaterial is still an area of significant research. There's been a number of different techniques, flame synthesis methods, plasma methods. Exploding wires was one of the first early ways in which the Russians were looking at making nano-aluminum, which was referred to as ALEX. A lot of the flame synthesis and plasma techniques make use of condensation process, nucleation processes. And another important area is actually, with particular control, is using wet chemistry methods, solution techniques, soil gel techniques to actually organize the material and have a significant amount of control over the system. So instead of going through all these in detail, what I want to just show you how one can group them. I'm providing you here with a number of references. But the first group that I refer to is really gas phase condensation processes. The idea here is where I start off with the material I want to make. And all I do is somehow gasify it. And what I'm really interested in is how it nucleates and how the growth mechanisms occur. So the type of processes that essentially fall in here, I could be looking at physical vapor deposition. I could be looking at this exploding wire where I say I start out with an aluminum wire. I create basically gas phase aluminum atoms, and then I just want to basically nucleate them, condense them to a very small scale. I can look at chemical vapor deposition and supercritical processing. And I'll talk about a couple of these. Group 2 then is where I'm going to make use of gas phase process, a condensation process potentially, but I'm not necessarily starting out with the material I want to make. So this might fall into the flame synthesis category, plasma or arc methods where I'm providing heat to change potentially the chemical composition. So here in flame synthesis, I might start out with a precursor compound that ends up making, the metallic atoms, and then I follow how they basically nucleate and condense. Say a group 3 synthesis method is basically wet chemistry. I'm using solution techniques here, where again I start out with a precursor, and through then solution chemistry, I have particles nucleate in the liquid phase, and I control their growth in the liquid phase. And I can do this through basically sol gel methods as well. A group 4 method here that one can talk about is essentially mechanical methods. These are traditional methods that have been used in the material science fields, methods such as ball milling and things like this, where I start out sort of a top-down approach, start out with micron materials, and through applying significant amount of force, I end up starting to make materials with nano features. And then the last group here I want to mention and talk about it is using lithographic techniques. Okay, these are patterning techniques where have essentially come out of the microelectronics industry, the MEMS field, and how one can actually use these techniques to make energetic materials. So I think with that, what I'll do, we can stop here for our break, and what I'll come back then is I'll show you some ways of actually making some very interesting materials that I talked about, and how they can be controlled and used to control reaction rates, ignition, and characteristics.